Now, the International Space Station is not only a laboratory in which science experiments are conducted, it's a test bed for new technologies that'll support future space exploration. And one of those new technologies is getting its first big test tomorrow. The optical payload for Lasercomm Science, known as OPALS, was delivered to the space station on the most recent Dragon cargo ship back in April. The OPALS team at the Jet Propulsion Laboratory in Pasadena, California, wrapped up the commissioning activities this past weekend. Yesterday, I talked with OPALS mission manager Matt Abrahamson about this project and the plans for the first optical downlink attempt, which at that time was planned for earlier today, Wednesday morning. And you will hear us reference that as he explains just how this experiment's designed to work. However, late yesterday, that first optical downlink attempt was rescheduled. It's now planned to take place tomorrow evening, about 8:22 p.m. Pacific time on June 5th. I started our talk by asking Matt Abrahamson where the idea for OPALS came from.
OPALS came from a couple different desires by JPL. The first desire was to develop a low-cost optical communications platform in space. So back in 2009, JPL had demonstrated an aircraft-to-ground laser communications link. And so the next logical step was to go up to low Earth orbit. And at about the same time, the International Space Station was looking for external payloads to operate on the outside of the ISS. So it was really a natural match to put OPALS up in space on the International Space Station. The second desire was for JPL to develop a flight projects program for early career hires. So these are hires that are within 3 years of graduating from college. And so everyone on OPALS, from the project manager to the lead scientist, is an early career hire.
Interesting. Something special for them to work on.
That's right. It gives much more responsibility to early career hires than they would typically get with other projects.
Let me take you back to the first reason. Why is there a need for an alternative to communicating with satellites, an alternative to doing so by radio?
It's all about data. We have too much of it. So our ability to collect data in space has greatly outpaced our ability to transmit it back to Earth. And so we're collecting all the scientific data, and we need to get it back to the ground. And radio communications have a limitation on the data rates that we can use to get this data back to Earth. And if we use laser communications, that really opens up the amount of data we can get back to the ground.
Well, what's the difference in terms of the quantity?
It's really a difference in terms of data rate, so it can go faster. If you think of the transmission path of getting data back to Earth, and think of it as a pipe, we're widening that pipe. So right now it's a very narrow pipe. If we widen that pipe, the overall flow back to Earth is much faster, and you can get much more material transported in the same amount of time.
I see. Okay. Let's help set the stage in terms of where this is. Where is OPALS located out on the station?
So we're on a platform called Express Logistics Carrier 1, and that's a platform that provides data and power to payloads on the space station. This is on the port side of the space station. So if you're on the ISS and you're looking along the forward direction of travel, we're over on the left side, and we're on the Express Logistics Carrier that faces the Earth. So we're down on the bottom. And we're down there because we require a clear line of sight with our ground receiver, which is in California. And so we currently have a window that's 110 degrees by 40 degrees, and that's where we're allowed to point our laser beam when we're transmitting.
And by allowed, you mean that's in order to make sure that you don't impact any of the other station components?
That's right. So we don't want to radiate our laser at any parts of the station. We also don't want to violate any regions where part of the station might rotate through, for example, the solar array envelopes. And we also don't want to fire at any location where there might be a docked vehicle, such as the SpaceX Dragon.
So you've been getting set for this first downlink. Have all the preps and checkouts through the weekend gone well?
They've gone exceptionally well. We turned on our payload for the first time on May 10th, and on that first turn on, all of our systems were operating as expected. Over the last few weeks, we've had a few other checkouts, one called an open loop commissioning test. That's where we test out our pointing capabilities to point down at our ground station. And then a closed loop commissioning test is what we just completed this past weekend. And that demonstrated that we were able to track our ground station very precisely, because a major component of this technology is to have very precise pointing to point this laser beam directly at our ground station.
Because Opal will have to rotate or tilt or one of those in order to keep pointed at the target as the station moves.
Absolutely, that's right. The station is in a relatively low orbit at an altitude of 400 kilometers, and it's traveling at around 7.5 kilometers per second. So when we pass over a ground station, we need to rotate at a speed of about 1 degree per second to keep a lock on our ground station.
So the first optical downlink attempt is on Wednesday morning. Tell us what is going to happen.
That's right. So Wednesday morning, we'll attempt to transmit a high-definition video over our laser link to our ground station, which is at Table Mountain in California. With our current predictions, we expect at 4:27 a.m. local Pacific time, the ISS will start to rise above the horizon relative to our ground station in California. And at that point, we'll fire a laser beacon from our ground station up to the ISS. A few minutes later, at about 4:30 a.m., the ISS is going to reach 25 degrees above the local elevation in the sky. And at that point, OPALS will initiate a sequence to point back at that ground station. And so it will attempt to lock onto that laser beacon that the ground station is sending up. And once it locks on, it's going to fire our flight laser back at the ground station. At that point, we'll have a bidirectional optical link, and it will begin transmitting our high-definition video at 50 megabits per second.
How long a pass do you get each time?
The pass is typically about 150 seconds, and that's really driven by that restricted window I was talking about before. The fact that it's only 110 degrees wide, we only have about 150 seconds where we can transmit. The ISS is above the horizon for about 6 minutes, but again, we only get about 2.5 minutes of that because of the restricted pointing.
Now, how long is it going to take for you folks to know whether or not the test is successful?
Well, we'll know almost immediately. So our first indication is we have a scope up at the ground station, and if we are seeing the signal, we'll see a very bright laser beam shining back down at us. And then about 10 minutes later, we'll be able to reconstruct the video on the ground. And if that video reconstruction, we're able to play it back, then we know that we're successful.
Will there be more tests after this first one?
Absolutely. This is just the start of our testing. OPALS is a technology demonstration, and so our whole point up there is to test out this technology, learn about it, and get some of the answers so that we can build a better, smarter optical communications system in the future.
And how might a system of this kind be used on future missions?
Well, it'll be used as a communications package or an antenna on future deep space missions. It will be kind of like the high rate option. So I'm sure that in future missions we will probably still have a low rate option that will be a standard radio antenna just for system safety. But this would be a capable system where we could downlink high rate scientific data to the ground when there's a bidirectional line of sight with the ground station. That allows us to get high-definition videos back, high-definition scientific data, and more scientific data than we're able to bring back today with our current antennas.
It's very exciting and eager to see how it all goes. Matt, good luck.
Thank you, Pat.
Matt Abrahamson is the OPALS mission manager at the Jet Propulsion Laboratory in Pasadena, California. And a reminder once again that the first optical downlink attempt for the OPALS payload is now scheduled for tomorrow, June 5th. International Space Station pass above the ground site in California lasts from 8:22 to 8:25 p.m. Pacific time on Thursday evening.